Okay, so I think that we need to maintain, like, so we need to upgrade the assumption. When you remove measurement independence, you need to upgrade the assumption of local causality, because the role of lambda is supposed to be to explain the correlations between the two wings of the experiment. If we allow lambda to just depend on x and y in a completely general way, it's not doing this, because you know, lambda could just contain a copy of x and y, right, and sort of not really be doing anything except containing arbitrary information about the measurement settings. We want to maintain the idea that lambda is mediating the correlations between the two wings of the experiment. So I want to argue like this. So we need a stronger assumption. So what I'm going to do now is specialize. So, you know, x and y are supposed to be free choices, right? So Alice and Bob are at liberty to choose them however they like. In general, they'll do that by specifying some joint probability distribution that they'll choose them randomly in some way or another. We're going to specialize to the case where they choose them independently. And also later on, I'm going to assume that these probability distributions have support on all possible values of x and y. It's not particularly important now, but we'll specialize to that case. Then we're going to derive the structure of the probability distribution. Once we've derived the structure of the probabilities, you can go back to more general ways of choosing. Okay, so the assumption I want to impose is lambda mediation, and this sort of literally says that the two wings of the experiment should be screened off by lambda. So B and Y are conditionally independent of A and X given lambda. Because conditional independence is a symmetric relation, we also get it the other way around. So what I mean by a local block universe ontological model for the Bell experiment is it's an ontic extension that satisfies this lambda mediation assumption. Okay, so first of all, we need to address two things. Okay, so we need to address two questions. Is this a sensible generalization of local causality? So I need to argue that it is. And then if I want to derive what is the structure of a local block universe ontological model, what consequences does it have for how the probabilities decompose? Okay, so I'm going to do some of these derivations. I'm going to use the semi-graphoid axioms. Those of you who are familiar with causal modeling will know these. It just simplifies some of the derivations in this case, right? So that I'm not going to do anything that you can't do directly by looking at the probability distributions. But this is a calculus which, from the perspective of here, from our perspective, is just a calculus of things that are true about the conditional independence relation. And in fact, this is a complete calculus for reasoning about conditional independences. So all of these things you can derive straightforwardly from the definition of conditional independence of a probability distribution. So we have symmetry, which I already referred to. Decomposition says that if X is conditionally independent of two things, Y and W, then it's conditionally independent of them individually. Weak union allows you to take one of these things and put it on the right-hand side of the conditional here. And contraction here, from the probabilistic point of view, has to do with the law of total probability. Okay, and in these axioms, X, Y, Z, and W, they could all be sets of variables, not just a single variable, including the empty set. So I can reason about ordinary independence just by, say, making Z the empty set here. Okay, so that it's from this perspective, it just simplifies the derivations, which are otherwise a little bit messy if you go directly with the probability distributions. Okay, so first of all, I want to answer, is this a good generalization of local causality? Well, first of all, it implies local causality. Okay, so it is a stronger axiom. And then in the context where we do assume measurement independence, it's implied. Okay, so what this result tells us is that it's an assumption which, when we drop measurement independence, includes local causality, but also includes some aspect of the measurement independence assumption that I believe is still appropriate to have in a theory where we have retrocausality. Okay, so proving the first part is easy. It's just an instance of this weak union. We can move something to the right-hand side of the conditional here. Because if I take this and move y to the right-hand side of the conditional, I get local causality. That's very straightforward. The other one is more of a pain. You have to, it takes several steps. So I'm not going to go through the proof in detail because it would just be too confusing, but it's there for completeness if anyone wants to follow it. Okay, so we have that we've specialized the case where x and y are independent. We have the no retrocausality and or measurement independence and the local causality. And then by a series of steps, you can go from there to lambda mediation. All right, so now we want to know what is the structure, what are the consequences of lambda mediation for the probability distribution. Right, since we've already proved that lambda mediation implies local causality, we know that we can decompose the probability distribution like this, only that we don't have measurement independence. But the point is that lambda mediation now has consequences for this term. It's not just a general lambda given xy anymore. So how do we derive that? Well, okay, so first of all, this is supposed to work for all choices of probability distribution that Alice and Bob might make. And it's very easy to see that if the prior probability for a particular value of lambda is 0, then all of these things have to be 0, and hence the whole probability is 0. So we can specialize, so that's true, and then we can now specialize to the case where we only considering values of lambda for which the probability is non-zero, and that will allow me to use Bayes' rule and divide by it, okay, basically. Okay, so if we start with lambda mediation and then apply decomposition twice, it means that I can delete A and delete B here. It tells me that x and y are conditionally independent given lambda. So what you can then do is take this term and apply Bayes' rule. So Bayes' rule gives me probability of x and y given lambda in terms of, well, like this. And then because of the conditional independence, I can write this as the product of two terms. And now I can apply Bayes' rule again to each of these two terms. That's going to give me all of these probability of x and y's that cancel. And I'll end up with this. Wait, your faces are in the way of the equation. Yeah, so I end up with this structure over here. So now I can plop that back in. And to clean this up a little bit, it's useful to take these two terms and move the lambda to the left-hand side by the definition of conditional probability, because then I can cancel out these two terms. And then I end up with this decomposition. For reasons that will become clear shortly, I've also multiplied it by probability of lambda and divided it by probability of lambda, but it's the same thing that we have up there. Okay, so that is the structure. Except it's wrong because I should have the lambdas on the left-hand side here. Okay, that's a mistake. All right. So note that if my prior probability distribution over lambda is uniform, then this just reduces to the product of these two probability distributions and then renormalized. Okay, and that's usually going to be the case in the model. In the models I'm going to show you in a minute. Okay, so that's what the structure says. Can this reproduce Bell correlations? Well, in order to formulate specific models, it's helpful to generalize this a little bit. So I'm now going to introduce a preparation variable. So the variable P represents the choice of what quantum state you're going to prepare in your Bell experiment, for instance. Okay, so, in an experiment, you may not always prepare the singlet state, but sometimes you could prepare a product state or some other state, etc. So that variable represents that choice. And now I'm going to have, the assumptions will be that all these three are independent. And then I'm going to have the lambda mediation assumption, but now I'm going to have, you know, because I've got 3 areas of my experiment, everything has to be screened off by lambda. So P is going to be conditionally independent of these variables and these variables given lambda. A and X is going to be conditionally independent of everything else given lambda, and B and Y is going to be conditionally independent of everything else given lambda. Okay, so you can redo the derivation. That's like, you know, it's more complicated, so I didn't want to make very complicated slides. But basically all that happens is if you go back to this formula, this probability here becomes lambda given P. Okay, so the general formula that you get is now this. And again, if we have uniform prior probability over lambda, then it's just the product of these 3 terms. And it looks exactly like you'd get from in the usual formulation with with measurement independence, except for the fact that these lambdas are now on the left-hand side of the conditional rather than the right-hand side of the conditional. Okay, I'm low on time. So I want to show you that you can reproduce Bell violating correlations in this way. These are like really sort of toy models, not supposed to be taken very seriously, but just to show you how it works. So the simplest kind of model you could do is for the Popescu-Roerlich box. So this is just a set of correlations that violates Bell inequalities more than quantum mechanics does, but it's still no signaling. But it's a sort of a simple model. So here, A, B, X, and Y are all bits. P equals box just means I set up the experiment to produce a PR box, right? And the probabilities are defined in this way, where this plus symbol here means modulo 2 addition. So 1 plus 1 is 0 in that case. And this is ordinary multiplication. So that's the condition. And I've also drawn out the table of values, that have non-zero probabilities. So if X and Y are either 0, 0, 0, 1, or 1, 0, then A and B have to be the same. And if X and Y are both 1, then A and B have to be different. Okay, I'm also going to use this notation here. So the square brackets Z given Fz means the uniform distribution over the values of Z such that Fz, the condition Fz is true. So I can also write this probability distribution like this. Right, so that's the PR box. It violates Bell correlations. And there's a very simple way of, dumb way of modeling this. We just let our latent variable consist of 4 bits. And those are labeled X, Y, and A and B because they're just going to simply hold the values of X, Y, A, and B. And then the probability of lambda, given that you're preparing a PR box, is just the uniform probability distribution over all lambdas that satisfy the PR box condition. And then these 2 probabilities for each of the 2 wings of the experiment, all they really do is copy the values of lambda into X, into X, Y, A, and B. So note that this model is retrocausal because if I marginalize over A here, the probability of lambda given X will be delta X lambda X. So it depends, the probability of lambda depends on the value of X and it depends on the value of Y. So that's where the retrocausality is.